I just wanted to say a word about Francis. Is that I first visited Orsay. I did my PhD on work at Francois Laudenbach, and I came here, I think it was pre-Francis, before you started, and I became aware of your beautiful papers with Jean-Pierre Autal in the early 80s. So really marvellous papers, and I think you express such beautiful geometric ideas. They're not easy to write them, but your papers are marvellous to read. So I really appreciate that, and that's great pleasure being here for this conference. So the first speaker today is Vladimir Fock, who's going to talk about higher Teichmüller groups.
Thank you very much. I would like to start to say that there are some, 99% of papers you read, you forget it. You remain, you take something from them and then you forget the rest. And there are a few papers that you read and they keep in your mind for ages. And for me it was the paper by Francis about the currents. And I'm still thinking about this paper even after then Francis explained to me that this paper is not as good as I thought, but I don't believe him. So what is this paper about? Is about the construction of certain function and on the square of Teichmüller space. And in Teichmüller space, I convinced that there are two kinds of questions. There are simple questions and complicated questions. So the simple questions deal with Teichmüller space as a real manifold. So, of course there are questions which are not yet clear, but many things are clear, and you can describe Teichmüller space really in a very concrete terms and work with it without, you can use many different techniques and get many answers. There are complicated questions which consider Teichmüller space as a complex manifold. And this is really something which is not yet well understood and really uncomparable. The understanding level is uncomparable with the level of understanding of real Teichmüller space. And the real structure, complex structure on Teichmüller space is actually equivalent to Weil-Petersson metric. So there are nice coordinates on Teichmüller space which exist for ages, but nobody ever managed to compute the complex structure in these coordinates. Francis' paper somehow solves this question, though not explicitly. And the idea is that you need to have some expression for Weil-Petersson metric. And I just recall for those who didn't read, and I recommended to read it right away if you didn't, because it's really a very nice paper. So you have a function of t times t. The Francis function, there is some explicit function t times t to r. It was actually presented several times already at the conference, but the main idea is that it has the following property that, first of all, if you take the limit of this function f.
Excuse me?
Pardon?
Sorry, which paper?
It's, what's the title? I forgot. For instance, what would you exactly the title?
Sorry, which paper?
About geodesic currents.
Geodesic currents and the dimensional state.
It's the geodesic currents of Teichmüller space. Well, you have a function which perhaps is denoted by other letters than f, and this function has the following property. First property, that it has a nice limit, then you tend Teichmüller space to lamination space. So in principle, you can take the function, the limit of, with respect to the first argument, of t times t to r. Well, appropriate limit, maybe I do not describe. With respect to the fourth argument, it's just a function. In fact, the limit is equal to the function of the space of lamination spaces, laminations. Well, it gives you a function L times, well, this equal limit with respect to first argument, sorry, L right of f is a function from L times t to r, and this is a just geodesic function. And, well, you can take the respect to the second argument, and you get the intersection of laminations. And the second property, the first property is the limit property, and the second property is that its second derivative on the diagonal, so you take d2 of f on the diagonal, is equal to y symmetric. It gives even more than information than just metric. It gives some function which extrapolates the metric outside the diagram. And I spent plenty of time in trying to compute this function explicitly, and I still do, but without much success. But my idea that, well, more or less computing this function, maybe I should not go into details, but more or less computing this function is equivalent to computing the complex structure on Teichmüller space. And now I have tried to explain that computing complex structure, it seems to me it's equivalent to some affine group business. And the idea of connection of these two subjects is the following. So you let's take complexification. So the Teichmüller space is a complexified. Well, if you complexify Teichmüller space, the question, what is this complex Teichmüller space? And the main candidate for this role is the space of quasi-Fuchsian groups. Since they were presented many times at this conference, I do not repeat what they are. So these groups, a descriptive group of SL2 to C. Then here we have well, as a real manifold, you complexify, you get a complex manifold, of course. The quasi-Fuchsian group is a complex manifold, but if you take, on the other hand, if you remember that T is a complex manifold, now the question, what is quasi-Fuchsian groups? And quasi-Fuchsian groups are, well, it's not only complex, but Kähler. So the quasi-Fuchsian must be something like hyperkähler. And so the question of finding complex structure on Teichmüller space is related to finding hyperkähler structure. So complex on T is equivalent, well, to hyperkähler on quasi-Fuchsians. And that was, Jean-Marc was mentioning this quasi-Fuchsian structure yesterday, but I will speak more details about this hyperkähler structure on that. I recall that hyperkähler structure is, in this particular case, I will also not go into details, but you can imagine that this is just three complex structure, so you have on this manifold three complex structure IJK. And such that they satisfy the quaternion algebra, I squared equals j squared equals k squared equals minus ijk. And in fact, instead of three complex structure, you can construct just a family parameterized by a sphere, and the well, you can just take the linear combination of these three complex structures, class CK, and this expression squares to -1, sorry, equals to -1, and this expression squares to -1 if a squared plus b squared plus c squared equals to 1. So you have a sphere of complex structure on your manifold. And having this sphere, you can reconstruct everything, well, all complex structures, all symplectic structure, and all that. So really, I imagine the hyperscalar manifold is a manifold with these three structures. So how one can approach to hyperscalar structure on the Teichmüller space? And the idea is close to what's done by Hitchin. So Hitchin introduced hyperscalar structure on the space of character varieties. So on the space of homomorphism of pi1 into SL2C. But we are going to use some another hyperscalar structure, though it's not as nice as Hitchin's because it's not defined on the whole space on the whole character variety, but we should not expect it to be on the whole character variety. We want quasi-Fuchsian group. So I cannot prove that it's defined on the quasi-Fuchsian. I can prove that it is defined on almost Fuchsian, which was definition given yesterday, but I would say just a little bit smaller space. But what is the construction? And the construction is really geometric and comes from the equation, which is my favorite equation on the Riemann surface. Namely, it's the equation relating it's generalization of the Liouville equation. So it's called Cauchy-Gordon or Sinch-Gordon equation. So we know the theorem that on every complex surface we can have a metric of constant negative curvature. It's very known fact, and this fact can be proven by considering the equation so you consider a metric. So if e to the phi dz bar is a metric on the surface, then the condition that this metric is constant negative curvature, you can compute the curvature, and the curvature is 1/2 dd bar phi, and you can equate it to the metric. Well, the curvature is minus that, so if you equate to the metric, and it's a Liouville equation, which is just constant curvature. Constant curvature, -1, curvature -1 condition. But you can modify this equation. So let T be quadratic differential. On sigma, then you can modify this equation and follow equate. 1/2 d bar phi equals to e to the phi plus tt bar e to the minus phi. So now I have a metric which is determined not only by complex structure, but also by a quadratic differential. So it's a generalization of the Liouville equation. And for t equals 0, of course, it's a Liouville equation. And also I write, well, you can modify it in two possible ways. So let's take another equals e to the phi minus tt bar e to the minus phi. So there are two versions of this equation. And both of them have certain geometric meaning. So I start from the first equation, and though maybe it's not very popular, but it has really very simple, you can deduce this equation for a very simple assumptions. So, sorry, dd bar phi. This is a condition that the metric e to the phi dz bar plus t dz squared plus t bar dz bar squared has constant curvature. It has curvature -1. So you just take the metric, which is not Hermitian. You add a non-diagonal term, and then require that it has a curvature -1. And then you get this equation. And the space of solutions, so therefore, the space of solutions is just the Teichmüller space. Because, well, you can of course prove it that it exists and is unique. The proof is automatic because it follows from the existence of harmonic maps between surfaces, so it's standard. So therefore, if you wish, this space of solutions, if you consider all possible complex structure on surfaces. So for solution of this equation, I understand the following data is just a complex structure on the surface plus metric on it plus a quadratic differential on it. So three data. So this space of solution is rather, if you understand that, well, rather not the space of the Teichmüller space, but the square of Teichmüller space. Because, well, you have initial complex structure and final complex structure, which is obtained by, well, induced by the metric e to the phi plus t bar. So this is a quite clear equation, and it has solution for any value of t, and you can do everything you want from
Sorry,
it. Yeah.
Is it true that the identity map will be harmonic map between the two metrics?
Right. Right. Identity map is not harmonic. And more, it's even not only harmonic, it's just minimal, actually. But yeah, it's harmonic. Sorry, it's harmonic. The identity map is harmonic. Well, it is obvious that it's harmonic because what is harmonic map? Harmonic map between two surfaces is harmonic if you take the metric, pull back the metric, and take it 0-2 part, and this 0-2 part is holomorphic. It's another condition. So here, just by definition, T is holomorphic. So its map is harmonic by construction. It's harmonic for any metric without any solution for that, but well, this condition requires that the metric is identical. This equation has a much more complicated meaning, geometric meaning. Well, not more complicated geometric meaning, but more complicated space of solutions. And this equation has the following sense, that it defines solution. So it defines a minimal surface and H3 quotiented by a discrete group by three-dimensional space. So a three-dimensional, I mean, well, it's a quasi-Fuchsian group. So if you have a quasi-Fuchsian group, you take a quotient of H3 by this quasi-Fuchsian group. This space is isomorphic as topologically as sigma cross R. Then among all the sections of this product, you may find the sections which have minimal volume. And well, of course, they always exist, but not necessarily unique. But if you have such a solution, then you have an induced metric on this solution. You have a second quadratic form of this solution. First quadratic form and second quadratic form. This is the first quadratic form, so e to the phi the first, and t is the second quadratic form. And first and second quadratic form satisfy Gauss-Kadatsky equation. And actually, this equation is nothing but by Gauss-Kadatsky for the e to the phi in t. So this is a quite straightforward question. So the space of solutions, at least, so the space of solutions is more or less the the quasi-Fock, well, it's in some subset, perhaps. This is a really big question, what's the relation between them, but it's at least a part, a big part of full dimension in quasi-Fock systems. What is very important about this equation that this it doesn't have solution for sufficiently large t. So I will write down here. Well, you can do the following. You can integrate the left-hand side and the right-hand side. And the integral of the left-hand side is just integral of the curvature, it's Gauss-Bonnet theorem, and it's 2 pi I Euler characteristic, minus 2 pi Euler characteristic. So 2 pi Euler characteristic of the surface. And it's the left-hand side. And the right-hand side is greater or equal than the integral of the surface of Tt bar, square root of that. This is a Cauchy-Schwarz equation. Cauchy-Schwarz inequality, that this integral is less than the integral of the right-hand side here. So you have this inequality, and you see that, this is other way around. You see that t is sufficiently large, then you have no solution for this equation. So really, it exists only in the vicinity of Teichmüller space. And, well, why this equation are interesting and why they're related to hyperkähler structure on Riemann surfaces is directed quite directly. And in order to show that, you need to interpret this equation. Actually, well, this equation is quite well known for integral systems. And of course, France is not a very good place to speak about integral systems, because every time I'm trying to speak about integral system here, then they may explain me that it's always the obsolete and nobody is interested in this integral system. And I'm trying to fight against this tendency, but since France is, well, it's not 100% French, so it's so it's related to integral system. And the relation is the following, that you can write this equation in an equivalent way. Well, I'll... So, the two equations, with this equation I would call Sin-Gordon, Foch-Gordon. It's Foch-Gordon. And this terminology, of course, from integral systems, and it's Sin-Gordon. Both of these equations are equivalent, can be written using spectral parameters, namely the CG and well, proposition, which can be proven by direct computation, but not very long, that CG and SG are equivalent to the following equation. So you take, so it can be written in a form of zero curvature condition. So dA plus A which A equals 0. Can be written in such a way where A is a connection on sigma with values and SL2 hat and here is a fine group. So the loop group, and this is a loop group, the space of functions. And well, in this particular case, I'll speak about just functions. So the maps from C star to SO2, which are not homomorphisms, just group with respect to pointwise product. And so the elements of this group write down as the matrix A of lambda, which is sum of AI, lambda to the I, and well, AI as just two-weighted matrix. And we also require, well, this is just my group. Well, since I wrote it in, well, maybe it should be written in it's an algebra. And not all connections give you solution for the Sine-Gordon or Cauchy-Gordon equation, but solution with some restriction. Namely, the restriction is very simple. You want that really this A first and second, you want that A be not very complicated. So A of lambda be the sum of phi times lambda plus A straight plus phi cross lambda inverse. So it's just polynomial in lambda. And you ask the following two requirements. First, the determinant of phi equals the determinant of phi cross equals to 0. So the coefficients at lambda be degenerate, and the second, and this is, well, this is a form, but so there are two components. Then you may require that both components are equal to 0, be degenerate. But in fact, it's equivalent to say just one is equal to 0, because once one is degenerate, the second is also degenerate for the zero curvature condition. And another thing, you take A of lambda, and you apply all possible involution that you can imagine. So you take bar, you take -1, you take minus, and then you conjugate your space, and you get A of lambda. So some condition which actually tells that your solution is not any solution, but some reality condition of the solution. So it gives, in particular, a relation between phi and phi cross. By the way, what is the cross is the following. Matrix cross, by definition, is equal to M conjugated, transposed, complex conjugated, and then you multiply from the left and from the right by the matrix, C plus minus, and C plus is, well, C plus is something like 1 minus 1, and C minus equal to 1, 1, and these are well, if you apply one of this condition, then you get Sine-Gordon. Another condition is you get Cauchy-Gordon. It's just in this very particular case, and the difference here in the rule how it's conjugated. So, well, this is some tedious computation. So you write generic form of this matrix, and then you substitute into this equation. So you have plenty of equations, because you decompose into powers of lambda. For every power of lambda, you give you its sort of own equation. Then you try to solve, you express one coefficient from this matrix out of another, and what you get at the end, you get essentially, well, all equations, plenty of them, 15, something like that, reduced to 2. Namely, one equation is just d bar t equals 0, and another one is Sine-Gordon or Cauchy-Gordon. So this equation is equivalent to the system of two equations, d bar t. So t is homomorphic, where t is and phi are certain coefficients of this matrix. I don't go into details. But the idea is that this equation is equivalent to equation from flat connection. And now how you can use, now it's, of course, in the integrable system business, this presentation is used to find solutions. Here we go other way around. we use this presentation in order to kind of describe the hypercarrier structure arising from this system. And this is quite obvious as a construction, namely, and this is kitchen, just kitchen idea to belonging to the kitchen. Well, once it's like, well, it's obvious once you know the answer. So the solutions of CG as G, let's denote it by, well, this space is mapped to the character variety. So if you fix one particular value of lambda, then you get a connection which is now not valued in matrices, but valued in matrices depending on lambda, but just in matrices. So we have a map to the space of representation of pi1 of the surface into SL2. And, well, C, maybe I should write here C. Explicit. But this map depends, so this map, which I'll denote by P lambda, it depends on lambda. Now, therefore, you have this manifold is complex. This map is not holomorphic, just a map because it's constructed using well, we impose some conditions which are not holomorphic to this one. So you have a family of maps to this representation, then you can pull back the complex structure. With respect to the complex structure, J. And then this is a family of complex structures J, P, lambda, star of J. So this family depends on lambda. You have just one family, of complex structures, and the Hitchin argument tells that it's actually hypercarrier family. This hypercarrier proposition, well, Phil's theorem by Hitchin.
Why does lambda live on a sphere?
Pardon?
Why does lambda live on a sphere?
Lambda lives in C star, but we can take limits and extend it. So it's extendable. Well, Hitchin is the complex structure extendable. For lambda belongs to CP1. So far, lambda is a parameter which is C star. And really, it's important that it's extendable to CP1, because if it were not, it would be the family which is kind of trivial. All complex structure would be isomorphic, because they just pull backs of one complex structure. But in this case, all these complex structures are all of them isomorphic by two of them, which correspond to 0 and correspond to lambda equals infinity. And they are different. And all that form you non-trivial hypercarrier structure, because otherwise it would, well, if you could define it would be defined for lambda equals 0 and well, this brackets, it's non-trivial. It's kind of family of complex structure, so you have a it's very similar actually for those who know the complex structure on quadrics. So we have a quadric. There is a hypercarrier structure on a quadric, and all the complex structure on the quadric, there are plenty of, there are two complex structures actually. Well, you have complex structures on the quadric, and complex structure as on a cone with blown up origin. So you have something like a cotangent bundle to a CP1. So we have cotangent bundle to CP1, which I'll denote just by cross, and So over 0, lambda equals 0, and lambda equals infinity. You have this blown up degenerate quadrant, and over all other points you have this, well, non-degenerate. And this is pure analogy with the hypercube structure rising on this space. Well, one remark that for also for specialists in Hitchin's hypercube structure, that Hitchin's hypercube structure is not this one. It's a little bit different. And the difference is the following: that Hitchin's structure depends on the complex structure of the surface. So you fix for once and forever complex structure of the surface, and his construction actually, Hitchin has another condition which involves this complex structure, which I didn't write it here. Hitchin's construction condition is replaced by this one. So this is a kind of another way to introduce hypercube structure which doesn't depend on this on complex structure on the surface. There is no basic point, so it's really something which is universal. Well, so all that was kind of motivation for my talk. So the outcome of that is, well, what I want to say, that it's very challenging to study the space of connections, well, the character variety of the surface, but with values not in a group SL2 or SL11, but with values in a group SL2 hat or SL1 hat. So that's and once you suppose you manage to describe some explicit way this space, you can solve this equation explicitly. You can find hypercube structure. You can work with substructures which are hidden from a first sight on the Teichmüller space, on the Fuchsian groups. Well, conjecturally, Fuchsian groups, but at least almost Fuchsians. And well, it will give some structure on this these spaces which are all of us scientists about. So my motivation is this. So now I want to say how to, well, I am asking a question, now I'm trying to partially answer this question. So how to construct explicitly this modular space and how to parameterize it as good as, in a way, as good as we do for to some extent, as we do for ordinary Teichmüller space, for the character variety, for character varieties with values and a finite dimensional subject. And the main ingredient to do that is, well, I will erase that. So, it's just some basic fact about affine groups. I wanted to mention it because it's quite important. So, the two faces of affine groups. SL and hat. So, one face is just the SL and hat, which is just the tensor product of the matrices. N times N, tensor of C lambda lambda units. It's one face, and the second face is that it's isomorphic to the following object. You take a matrix Aij, which Ij are in integers, arbitrary integers, not only from 1 to n, but with with the condition, which is Ai plus n, j plus n equals I plus ij. So we have a matrix which is periodic with respect to a matrix. You can cut this matrix into n by n blocks, And this block is equal to this block, is equal to this block, etc. So it's invariant under the diagonal shift. And this space, of course, you need, for technical reasons, impose some condition, because in general you cannot multiply it with infinity, because multiplication gives you infinite sums. The simplest possible way to get rid of that, perhaps sometimes it's not as it's too strong, but I impose that condition that ij is equal to 0 for I minus j large enough. So you have a matrix which is 0 far away from the diagonal. Now you have this matrix which is periodic, and let's denote this matrix by A0, this by A1, this by A minus 1, etc. And the correspondence is is the following, that Aij goes to the sum of Ai lambda to the I. And exercise that this is a homomorphism of algebra. So if you multiply periodic matrices, this is the same thing as if you multiply matrices which are debatable now. Well, there are plenty of, well, it's a basic observation, then you can play something about, you can consider quasi-periodic matrices. In that case, you get central coextension of this group. Well, but the main observation is just this one. So, the moral of the story is that affine equals periodic.
Could you say the correspondence? I'm sorry.
Pardon?
Aij goes.
You take an infinite matrix,
Yeah.
and you get a finite matrix, where I is taken from this picture.
Okay.
So you cut into the blocks,
Yeah.
n by n. Of course, A0 stands for on the diagonal. This is main diagonal of my matrix. I take blocks and then take one row, which determines the whole matrix. And then maybe I should write also that if you may, okay, maybe I should, well, you can get central extension also in this picture, but I don't co-extension, but I don't want to speak about that. I don't really need it too much. So now how one can use this observation in order to construct something which is moduli space of the moduli space of character coordinates on character varieties for affine groups. And the rough idea is the following. So, another recollection, I just recall that coordinates. So, what is a recollection of coordinates? Coordinates on graph phi1 of sigma to SL2M. And also, you need to take something, some ramified cover of that in order to have good coordinates. SLN, sorry. SLN. SLN. Over any field, so I don't know precisely which field it is. So you have, or on Teichmüller space as well. So it's sharing coordinates on Teichmüller space. But I just want to introduce notation more or less using. So how you do that? So in order to do this coordinatization, you start with coordinates on flags. So you take your SLN, you quotient by the Barossa group, so you consider flags. It's just flags. complete flags, you take n power and you quotient it by SLN. And on that you can introduce explicit coordinates in the following way. And also I will present maybe roughly the situation then little n is equal to 3, sorry, and big N is equal to 3 as well. And this is, well, by abelianization. So, what means by abelianization? Means that you take well, it's also, well, coordinates. It means that it is a part of this line. So you introduce coordinates on the space of maps to SLN by identifying it to certain map to abelian group. And then for abelian groups, everything is trivial, so you get, well, maps of representation of pi1 of something into abelian group is just a torus, and you can explicitly write this torus and use that to interact. So you need really to pass from non-abelian group to abelian. And how it does, and it can be done for just not only for representation space, but also just a collection of flags. And the idea is the following. So yeah, I'll recall the construction. You draw a picture. So I recall the situation that you have 3 flags in honest talk. So you have just collection of flags in the space. So this will be the collection of 3 flags in 3-dimensional space. Or projectivized way, you have 3 points on 3 points and 3 lines passing through them in the projective plane P2. Well, P2. It's just a picture in R. In general, it's just our initial P2. Then you do the following. What does this picture mean? This picture means simply that I can draw, these circles, points, correspond to points here. So on this picture you have 6 points. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Maybe it's the best way to enumerate. 4, 5, 6. And here you draw 1, 2, 3. 4, 5, 6. So you have for every circle you get 1-dimensional space. On this left picture you have a 1-dimensional space. Namely, it's a projective picture. You have points, but you should remember that in vector space you have lines. So points, or rather, which is equal to projective in P, I write C2 in the vector space. Lines in C2. And what are black points here? Black points are the relations between these lines. So black points, for example, let's consider this point. Let's consider point 5, 4, and 3. So 5, 4, and 3, these 3 points belong to one line. So therefore, if you have the 3 points, you can take the sum, direct sum of these 3 lines. So you have line L5, you can add with L3, you can add with L4, this space is 3-dimensional, but all 3 lines belong actually to a plane. because on this picture they stay in the line. So you can map it to just to the sum of these two, not direct. You have direct sum to this is dimension 2, this is dimension 3, and therefore there is a kernel of this map. And this kernel you associate to this vertex. Maybe I should draw. This is now a cover because it's not a part of the picture. So, therefore, what you get essentially, so these are, black points are relations of relations means that claim that the neighbors of this black point are not in general position. It's this structure which is known as matroid actually. And so, but what you get one-dimensional vector space associated to white points, one-dimensional vector space associated to black points, and of course there are also maps associated to edges. Because if you take direct sum of this kernel, definitely maps to L5 and 3 and L4. So you take something non-abelian or something in SLN, it's not in connection, just configuration of flags, and you produce something abelian, connection on a graph. So maybe I shouldn't, well, I have no time to go into details anymore, but I want to say that it can be done for, first of all, it can be done for any number of flags. So we can take you can define, well, this is the same way you can introduce coordinates on any collection of flags, and of course you have infinitely many flags, you have an infinite dimensional space, and what's the relation between, so you can, well, if you have number of flags in infinite, then number of flags in infinite, then you get the infinite dimensional space, of course. But you can impose certain periodicity condition. So the representations of pi 1 claim pi 1 of sigma to SLN is equal to the space of flags to the power, for example, Q1 such that there exists a discrete group delta in SL2Z such that f of g of alpha equals gf of alpha where g is in delta and H2 quotiented by delta is my surface sigma. Well, what I claim is the following, that how one can imagine the representation space as an infinite collection of flags. So you have QP1, and every point you have a flag. So you have every rational point you have a flag. You have flags everywhere. But you require that this configuration of flags, of course this is infinite dimensional, but you require that it be symmetric. So you impose the condition that if you rotate the picture but by an element of SL2, a certain subgroup of SL2Z, then you get the same configuration up to diagonal action of the group, which is given by rho of G. So rho is the delta 2 to SO2 to and Fg is just flag associated to, this is the alpha, and this is the f of alpha. So we have configuration, but it's invariant under the group, and the space of configuration invariant under the group action is actually the same thing as the representation space. So really, the configuration is determined by rho. This is the main observation. So the configuration is determined by rho, and then therefore you get this isoborg. So why I explained all this construction? Because this construction kind of ready to generalize to a affine case. And a affine case, so I just very briefly maybe define the space. So a affine case is the same thing. The difference is that you replace a affine case. Well, you can do very simple thing. You just take n goes to infinity. So you consider flags in infinite dimensional space instead of finite dimension. Of course, if you go that, you lose your finite dimensionality, because there are, well, the larger is n, the more complicated is your manifold, more is higher the dimension. But you can impose the certain, but we are speaking not about infinite dimensional group, but about affine group. And affine group is infinite dimensional but periodic. So you impose the additional condition that for any alpha and beta, there exists an operator lambda alpha beta, which maps your C to infinity, C to n, which n tends to infinity, to C to infinity, such that f alpha I lambda alpha beta equals lambda equals f alpha I plus m, and lambda alpha beta f beta I equals f alpha I minus n. So you have your flags, and you impose the formula. Sorry, maybe I should define that f alpha I. So what is a flag? F alpha I is just a collection of, well, it's something sitting in f alpha I minus 1, etc. So my flag, just lower index is just number of flag, and upper index is the dimension, codimension. Well, it's not codimension, but something in the dimension of replacing codimension. Well, you impose some additional symmetry.
So what are alpha and beta?
Alpha will be still the point of QP1. So in every point you have infinite dimensional flag. But this configuration you impose two conditions. First, invariant under the group delta. And in this case, you essentially put your configuration on your surface. And second thing, you require periodicity. Namely, you can raise the dimension of one, you impose the existence of operator which commute with each other. Sorry, all these numbers commute. And such that you can raise the dimension of one flag and at the same time, decrease the dimension of another flag. And in infinite dimension, there are operators which change. Well, you can map this space to its proper subspace. It's not a problem. So you may vary the subspaces, and in this way, and the claim final, well, which I can claim for sure, that this finite dimensional space with mapping to group action, etc. So it defines all this construction. Defines a finite dimensional space with mapping to group action. And there exists a map of this space into the space of affine connections. Though, well, property of this map is not, the fact that it's embedding is not yet proven, but I agree with that. It's just I should mention. So it's mapped to wrap phi 1 of sigma through SL2 SL1. So this is a candidate for a space which generalizes. And well, what's nice also about this space is this is exactly twice as large as the space of homomorphism to SL2, to SLN. And so what we expect from this affinization, because, well, we want to construct hypercurl structure, so the space should be twice as big as the dimension of the original space, so it's complexification, so this dimension is 1. So that's, well, thank you very much for your attention.
So any questions or comments?
Is this space of periodic flux an orbit of a loop group or of the extended loop group or?
No, you have. No, on this space of periodic flux, there is no group action, if you wish.
For fixed alpha, there is no group action on the space of flux attached to alpha.
No, you have. Sorry, one moment. No, sorry. You have a loop group. Sorry, maybe not. I'm a little bit after that. It's made. I think it should be, but I cannot prove it right away, in a sense. So the construction of a map from these configurations to a representation of a affine group is kind of non-direct, but there should be more direct. There should be action of the affine group in the space of no, sorry. Maybe I should. Well, in the fine dimensional case, you already quotient it by the group action. So the relation of that. So on these pictures, for example, you have no action of the SL2, SL3. Now it's pictured on the projective plane, but you consider configuration up to the action. So there is always all the group is already quotient out.